Okay, it is time. Finally, we're going to do some programming stuff in this class, okay? I know it's a math class, but we're now getting to algorithms and algorithm analysis. And oh man, is that beautiful. Are you ready? So let's do this. It's a lot of stuff, but they all go together, so it's a bit of a shorter lecture, or a shorter set of slides than the last one. So yeah, let's get started. Algorithms. We know what this means, right? So all an algorithm is it's just a step-by-step way of solving a problem. It is a recipe. So you have your flour, you have your milk, and you have your eggs, and also baking powder, and then you make pancakes, right? That's essentially an algorithm. It's like, okay, take this, these things, and then here's a list of operations for you to do to create your pancakes, right? That's the idea. That's all an algorithm is. It's a step-by-step way of solving a problem, and we would like to treat it just like we've treated everything else in this class, with a ton of math, right? We'd like to formally reason about the programs that we write, the algorithms that we write. So we need to talk first about like what it means to execute code. And we'll use pseudocode as an example because that's what your book likes. And well, how can you reason about code? It's like I have, x equals 4, x equals x plus 1, etc., etc., etc. Like if statements, loops, and things. How do we reason about the way our program looks at a certain given point in time? Like this is line 1, this is line 2. Like what does it mean, like to have information about our program on this line and to know what's changed after this line is changed? Okay, it's possible to do this if we don't allow functions, and let's make it easy on ourselves and not allow functions because otherwise we have to model the call stack. Let's just say that the state of a program is the values of its variables. So, for example, there's only one variable in this program, so we can just keep track of it in our state. So the state at this line 1, it is after line 1 is executed, the x variable holds 4. Okay, that's fine. Maybe there are other variables, but that's the idea. And before the program, x didn't even exist. Then after this second line, the state is now x is whatever it was plus 1, but we know what it used to be because we have the previous state, x is 5. Yeah, that's how we can keep track of our program and how it's executing. Okay, and this is the beginning of how to do this for real, to analyze programs. We have to keep in mind, like, what does it mean for a program to be executing? What is it even doing? Okay, the state is changing. That's the point. Oops. Okay, so for example, for assignments, that's pretty easy. They make a new state by altering one variable in the previous state. So x, whatever x was before, like if this was up here the previous state, maybe it like had x 42, y 7. The new state, the one that happens after this line, I don't know, let's draw the box over here, I guess. New state, that is going to be, okay, well, y is getting set into x. X becomes whatever y was, so if y was 7, x is now 7. That's the new state of the program. Okay, that's what an assignment does. It just figures out whatever this is in the old state, and in the new state, it changes the x variable to be whatever this side evaluated to. Okay, not too bad. It's just the concept of state might be new to you. Just keep that in mind. That's what it means for your program to be executing. That's what it's keeping track of. It's state. Okay, now we're ready for if statements. I'm sorry if this is like super obvious to you at this point in your programming career, but it's good to just spell it out. Feel free to fast forward. Okay, so if statements, they execute code if a condition evaluates to true. So whatever you put here better give back true or false eventually, and only if it's true do these lines get executed. Okay, so the idea is like first test the condition. If it's true, execute the body, all the lines of it. If it's false, you skip over. You skip over the true case. There might be an else case. Do the else case, if there is one. And after you're done with one or the other, you just continue the program. The rest of the program happens. Okay, so that's how an if statement executes. It's first going to check the condition, whatever it is. That's going to mess with the state, maybe, if you call a function that does weird stuff. And then it's going to execute the body. That's how I want you to think about this code executing. If you've never had it explained like this, this is the way to go. I promise. Okay, so yeah, that's if and if else. You can have an alternative if the first thing's not true. Okay, so they execute the true branch if the condition evaluates to true. So that's the very first thing it does, is evaluate the condition, and the false branch gets executed if there is one, and the condition evaluates to false. Now, technically I'm already saying that there is an else statement here. Okay. Otherwise it skips if it's if. Otherwise it does else if it's if else. Okay. So that's if else. Not too bad, right? While. This is a loop. So a while loop repeatedly executes this body as long as the condition is true. So let's spell that out. Let's draw it. So again, like an if statement, it's going to check the condition first. I'm going to make it small up here. I'm going to call it cond. If it's true, it does its body. And then it goes back to the condition checking. This is the loop part. You see that? That's what it means for a while loop to execute. And the second it's done is when the condition becomes false. Then it does the rest of the code. The stuff down here. Yeah. It only happens once it's false, though. It's always check the condition, do the body if it's true. Come back to check the condition. Keep doing the body if it's true. That's where the loop happens. You see the loop-de-loop now. Okay? That's how a while loop executes, and that's how we can formally reason about it, because we know it's going to do this. Okay? We know that the second the while loop is done, that condition is false. Okay? That's the idea. Once the condition is false, the loop is stopped, and so we know it's done. Okay? So a nice way to think about this, especially when we're proving things later about programs, is if a loop ever stops at all, that means that its condition must have become false. So whatever this long thing was here, we know down here, it must be true that not condition is true. Yeah? The condition became false if we're ever getting below this. Otherwise, we'd have an infinite loop. Yeah? So that's I think all I wanted to say there. Not too bad. I just want to show you these flowchart forms if you've never had that shown to you before. That's very important. And so yeah, your book also talks about for loops, so do read it, but they're pretty much a while loop in disguise, so I'm just not gonna spend any time on them here. Okay, so now something a bit different. I'm not asking you to like unroll definitions, I'm asking you to be creative. So here is an algorithm that I want you to write. I want you to write the pseudocode for it. Solve this problem for me, however you feel like it. Okay? And I want you to use pseudocode just to get examples with that, because we want to make our programs look like this, not any real programming language. We want to make it so that they could be any programming language, and they could be translated to Racket just as easily as they could be translated to C++. Okay? So here's the program that I want you to write. Go away and write it for a little bit. Okay? You're given a sequence of numbers. Maybe it's a vector, if you want to think C++, but you have indexable elements, A1 through AN. So not even starting at 0. You see how this is pseudocode, right? And then you have n, which is the length of this sequence. Okay, you're given that as well. So maybe you're given an array instead of a vector, and you know how long it is, no matter what. Okay, and your output is true or false. It's a Boolean output. True if you can find two numbers in the sequence whose sum is 0, and false otherwise. And I should be a bit more specific here. Let's say two separate numbers in the sequence, because technically you could choose, like if A2 is 0, you could choose A2 twice. Let's disallow that. Two separate numbers. You have to add A1 with some other A I, okay? Not A1 again, okay? And so you want to find two separate numbers in the sequence whose sum is 0, and if you can find that, return true. Otherwise, return false. Okay, so that's your job. Come up with an algorithm. There's an easy way, and then there's an O of n way, a linear time solution, which is wonderful, and I would be happy to talk to you about it in office hours. Okay, I don't want to waste time here with it, but it's really cool, I promise. Okay, so yeah, give this a try, and then I'll come back and show you the less efficient way, but the way that's easy to think about. Okay, so as far as loops go, we're going to have to loop through this. Let's pretend we have a for loop now. So this is the idea. We're going to say like for, let's say I equals 1. It starts at 1 to n minus 1. You know, let's do it to n right now, and then we'll simplify it later. So we need an index into our sequence because we need to find two things, right? And they don't have to be right next to each other. So I'm going to eventually need two indices. I need to have an I, like this is my AI, and I need an AJ as well, right? And I'll see if they add sum to 0. Yeah, that's the idea. So for I equals 1 to n, for j also equals 1 to n. And then we will say if AI is summing that with AJ, not BJ, sorry, AJ, if that equals to 0, then we should return true. Okay, and then if we tried all this whole thing and nothing worked, we should return false. That's the algorithm. Did you come up with that one? So it's essentially pick two indices, try them, and see if they sum to be 0, if they did return true. I guess technically you should also check that that I is not equal to j, because we don't want to use the same one twice, but there's a better way. Okay, this is slightly inefficient because notice that I can become, like, you can try, how do I want to say this? You can look at A1 and A3. Let's pretend that I equals 1 and j equals 3, and we'll sum them together and see if they're 0. The loop does that, but it also does it like this. Like, I can be 3, and we're looking at A3 there, and j can be 1, and we're looking at A1 now, and we're adding them together again. So that's duplicated work. Duplicated work. Let me write this somewhere else. So that's silly, and there's no need to try it again when we've already tried it. So maybe let's keep the idea where the I variable is holding the smaller one, because the reason whenever we try it again, I is bigger than j. Let's just make sure that I is smaller than j, and that'll make it so that we don't duplicate our work. Okay, so the way that you can do that is you say you force j to always be smaller than I. Yeah. Or sorry, you force I to always be smaller than j. You force j to be bigger. So no matter where you're starting, you start j at 1 bigger than I. Okay? So no matter what I is, if I is 2, the next possible value for j is 3, because otherwise we'd allow like the swapping to happen. We don't like that. Okay? That will help. And then we want I to go to n minus 1, because we don't want to repeat anything. Okay? So the last thing that we try is I equals n minus 1, and then j equals I plus 1, which is n, and that's the last pair we try. Okay, that's the idea. So that's a lot of talk. That means that we don't have to check, we don't have to check this anymore, because it's guaranteed for I to not be j. And this is slightly more efficient because it's going to like skip half of the tries. Otherwise, it would have done the same thing twice each time. Okay, So this is the algorithm, and we're going to get into running time analysis soon, but you should have seen at least a little bit from CSCI 41. What is the running time of this algorithm? Well, in the worst case, this is practically n. It's going n times. And in the worst case here, like it's very close, like I is equal to 2 or something. Well, that's also practically n times in the worst case. So my hand-wavy solution is, okay, this is constant down here. It's this is O of n squared, complexity, where n is the size of the sequence. There is a way to do it in linear time, in fact, and I encourage you to think about it. Do come to office hours if you want a hint. But here's the algorithm. This is pseudocode, and we kind of reasoned about it. Okay. Now let's get fancy with the growth part. Let's understand big O a whole lot better than we did before. Now, let us hit that hard. So, asymptotic growth, it is usually, I mean, you talk about this in terms of like mathematical functions, right? It's like, oh, here's the asymptote. It's not getting any bigger than this function, right? We can use this to programs. We can apply this to programs, okay? That is the idea. So the asymptotic growth of a function is just a measure of how fast the output f of n grows as the input grows, okay? So it's a bit different than the mathematical definition, I would say, the one that you're used to already, maybe. Our definition for this class is going to be a bit more general than that, okay? But the idea is important still, because asymptotes, they bound things. They bound this function. It's like it's never getting bigger than this thing, than this y value. That is quite nice. We would like to simplify functions in the end and gain accurate bounds for our functions at the same time, okay? So as programmers, here's the idea. We don't really care about how fast a function's growing, because there's an infinite amount of functions that look like this. Like, okay, here is y squared, here is like, or sorry, x squared, here's 2x squared, here's 3x squared or something. They all look essentially the same. We like to compare things, okay? There are an infinite amount of different yet similar functions, and we'd kind of like to lump them together. Like, these are all essentially the same thing, and from our point of view as programmers. So what we do is we lump those similar functions together into, you guessed it, equivalence classes. What? And so we can treat them the same and look at them the same. And this is why I had to drag you through last lecture, talking about these things. So the different kinds of growth that we care about are usually big O, big omega, and big theta, okay? We don't say capital, we say big, all right? Which is weird. And these are the ways that we talk about asymptotic growth of functions. We can use other functions to bound other functions is the key. That's what we're going to do. It's like a generalized kind of asymptote. We can use we can use functions to bound other functions. That's where we're going. Okay, so back to where we were. Yes, it's recording, cool. Big O. You've seen this. You've seen this in 41, but you might have had this, had a very like hand-wavy definition given to you. We're going to give the real one this time, okay? So big O notation looks like this. It's like we say f equals O of some g. And we read it as f is O of g or f is big O of g. Okay, this is how we write a relationship between two functions. This kind of big O relationship, f is big O of g. And the way that we've defined this before is something like, okay, f is always smaller than g. G is the upper bound, okay? G of n is way up here, like here's our f. And g is cool, and it's very close to f, but it's like, it's always bigger. That's kind of the hand-wavy CSCI 41 definition. It's like, okay, it's f of n is less than g of n for all these n when you drop constant factors and only worry about large n values, okay? That's the idea. And if there's only a constant difference between these things, we call it O of 1, constant time, which is kind of different because you don't usually think of functions like this, but really, O of 1, it's just define g of x to be 1 forever. That's the idea. Okay, so the real definition of big O now, you're ready for it, is, okay, we have two functions, f and g, and they take integers to real numbers, okay? Positive integers to positive real numbers. That's not technically necessary, but it's the way your book does it, okay? Then we will say that f is big O of g if there exist, oh man, this is why we had to learn so much math to get here, if there exist constants, c and n naught, such that f of n is bounded below, it's always less than or equal to c times g of n. Okay, we get to multiply g of n by a constant whenever n is greater than n naught. Okay, so this English can be translated to this math. There exists a c greater than 0, and there exists an n naught, such that for all n greater than n naught, f of n is less than c times g of n. Weird, right? But all it's saying is that g is an upper bound for f if you multiply it by some constant. The idea is there is a point at these functions where they meet, f of n, and then you pick your fancy c, pick a good one, and that's c times g of n. Okay, so it's been scaled. Like maybe this was g of n right here, but c times g of n looks like this. Okay, there's a point where these meet. That is the key. And from that point onward, g of n wins. C times g of n wins. It's always bigger. There's always a gap. There's always this gap. Or they're right on the money, okay? Or they're equal to each other. That is what it means for two functions to be related under big O. We say that the second function, the one that's inside of the O, it's almost like it's a function call itself, that is the upper bound. G is an upper bound for f. So for example, if you had f of n equals 2n squared, it is definitely O of n squared, because you can choose let g of n equal n squared. That's the idea. And then c, let c equal, I don't know, 3. It's bigger. It's always going to be bigger. Yeah? You see that? That's the point. And then same for these, and cubed and n fourth, those are obviously always going to dominate n squared after a while with a good constant. Okay? The constant's key and the n naught's key. It doesn't have to be bigger at the start. They can like wobble between each other, but eventually c times g of n must win out. That is big O. Okay? That's the real definition. Hopefully that's making some sense. That's all you really need to know. There is some intuition that we could give you, and let me try. All right. So the idea is you kind of think about big O as saying that f is bounded above by g up to a constant factor asymptotically. That's how you want to think about it. And so again, for example, let's do 2x squared. F is O of x squared. You see that? It is O of x squared, because you can choose c to be 3 again, yeah? And that would make the function, just x squared, dominate 2x squared, because you can multiply it by 3. And so that is the idea. So the concept or the intuition comes from zooming out on the graphs of these functions. Like you have f of x equal to 2x squared and g of x equal to just plain x squared. When you zoom out, these don't look very different, and that's the point. That is the point of big O. That's really the point of big theta, but we're going to get there. Don't worry. So let's use this really cool graphing calculator to show some stuff. Okay, so here it is. Let's make this all pretty. Let's say here's our first function, y equals 2x squared. Bam. That's our first function. That's f. And now g is y equals x squared. Yeah? So let me show you that they're not too different from one another when you start zooming out. Whee! You see that? About there I can't see any difference. They look like they're right on top of each other. You see that? That is the point. And I wonder if I can change these axes a little bit. I sure can. I don't know what I want. Negative 1,000 to 1,000. No, even more. Oh, sorry, not the y-axis, but the x-axis. Excuse me. Let's do. That's better. So yeah, you can keep zooming out. I guess that didn't really help. But essentially, they're the same. They're the same function. And so that's why we kind of drop those factors, those constant factors that are out in front. We don't really care about the 2. It's O of x squared. Not a big deal. They eventually become the same. Alternatively, if you've taken calculus, you can say that f is big O of n when, making n large, f of n over g of n, where g is going to be your function that you're saying is the upper bound, it's less than infinity. It doesn't have to be 0. It doesn't have to be infinity. Or no, wait, if we're saying that g is the upper bound, it doesn't have to be 0, my bad. And the point is, like, maybe the function's slightly smaller, and the limit for our example is 2. It's less than infinity, though, okay? Which means that there is a constant somewhere. That is the point. So, yeah, the idea is that g is able to bound f so that the ratio between them doesn't run away. That is the point. That is big O. Okay, so yeah, you've seen it before, but now you're an official expert. So again, with the rules, those 2 rules, you drop your lower order terms, and then you drop constant factors, because you can always find a g that works. Okay, so here we go. Here's f of x, 2x squared minus x plus 3. And so the first thing that we do is drop lower order terms, and then we drop constant factors. So the g of x equals, dun dun dun, let's see here, it equals just x squared, right? That is what it is. That is, let me say that f is O of x squared. Yeah? That is the idea. So we have to follow the rules, though. We need to find the c and the n naught, okay? G of x is this. What's c? What's n naught? So what's the constant factor that we multiply g of x by? Let's just pretend it's 3, and then let's find our n naught such that 3x squared is bigger than this original function. Okay? So here we go. I wonder if I can just reload the page and the axes fix themselves. Yeah, much better. Okay, so here is 2x squared minus x plus 3. And then this one can be 3x squared. This is the world's greatest graphing calculator. Okay, so it looks like it found that. I was very happy about that. It found it. Do it again. Yeah, thank you. So it looks like this is where they meet. The blue one's the one we care about. We want it to be bigger. And it looks like it's always going to be bigger. Like it's way up there. Like, ooh, way up there. Way a huge gap for every x value. It's always bigger right after here. Wherever this is at x equals 1.303. So let's make, I don't know, let's make n naught 2, just for good measure. Then it's always the case that our values of 3x squared are bigger than this one. Okay? Because the value at, like, for example, x equal 2 is, for the first one, it is 9, and then for ours, it's going to be like 12. Okay? It's always going to be bigger. That's quite nice. So that's the first one. That's the first example. Okay, let's keep going. This one. Let's follow the rules to find this one now. I guess technically I didn't have to give the c and the n naught, but at least it was good to prove this first one for posterity. Also give c and n naught for this one. We'll we won't take our time as much for these other two. Oops, subscript. Okay, for this one, we need to, drop lower order terms and drop constant factors. Ooh. So this is where it gets a little tricky, because I have like log base 2 of n here. Again, what? Like, maybe it's just log base 2 of n? I don't know. The trick is to notice that there's an n multiplied here too, so it makes this function bigger. N times log of n is bigger than just log of n, okay? And they go together. Like, you can't combine this into here. Doesn't make sense. Okay, that's the idea. So do that. So this goes away, and then we drop constant factors from this one, and n is not a constant factor. It needs to stay. It makes the function bigger, but we can drop the 5, okay? So we say that f is big O of n log base 2 of n. Okay, that's the trick. All right, how about this one? What do we think? Well, we're going to drop lower order terms. This is a lower order term, believe it or not. There are no x's multiplied by it, and so eventually, even though this is a giant number, when the function gets large enough, when we're way the heck over here for like giant values of x, this number doesn't matter anymore. That is what I want to get ingrained in your mind. I'm sure you've already had it ingrained in your mind if you've like studied limits, but again, constants mean nothing in the long run when x gets very large. That's what we care about. Okay, now we drop lower order terms. 15 goes away. I tricked you here because 42 is there. Let me get rid of the 27. And so 42 wins out, and it's 3. So f is big O of, oh shoot, I said f of z here. F of x. When x, it's x to the 42, okay? And trust me, you can go and find n naughts and c values to make this work, I swear. Okay, that's the reason big O is a thing. It's a lot easier to talk about this function than to talk about this function, okay? But they're, for all intents and purposes, the same. They are related. They're all in this equivalence class, okay? Several functions are in it. Okay, another example. Hello, sorry for the weird edit. I would like to re-explain this slide because I don't think I did it well enough the first take, so you're welcome. So here is a function, f of n, and we'd like to prove that it's O of n cubed using the definition, which means we need to find a c, we need to find an n naught, and we need to make sure that these work. We have to do a real mathematical proof this time, okay? So we got to find an upper bound. We got to prove that this is an upper bound, okay? So let's do it. We'll use the definition, and this is harder than just looking at a graph, because here are these two functions. It looks like actually blue is barely winning. Like, how do we know? How do we know this is all going to work? We don't really. So, or maybe like we pick a random number like 3. Is it really, is this a good enough proof? Not really, right? So that's not good enough. We could then turn to programming. So I wrote this program, and here is like a racket program with F and G, and you can pick like C to be 3, and you can test all of the values of F and G between like 1 and 1,000. That's still not a mathematical proof. Like, okay, it works. G is bigger when you multiply it by 3, but how do you know? Like, is 2 really the answer? Like, from 2 onward, does 3 times this function actually work? And the answer is still we don't know. So here's how you do it with real math. Okay, so here's what you can do. You need to find an upper bound for this. What can you multiply n cubed by? And let me show you the trick. 2n cubed minus 4n squared plus 7. That is always going to be less than or equal to 2n cubed plus 4n squared. You see what I'm doing? Plus 7, because n is going to be positive, or at least not negative, and that's going to be less than or equal to always, or sorry, not always, but watch me do this. 2n cubed plus 4, not n squared, n cubed, plus 7, n cubed. And this works when n is greater than or equal to 1, right? As long as n is greater than or equal to 1, this is always less than this. Yeah, less than or equal to. Nice, huh? So then, this is equal to 2, 4, 7, that's 13, n cubed. Look at what I just did. I have mathematically shown that c can be 13, bam, and naught can be 1. As long as n is greater than or equal to 1, this holds. This less than or equal to holds. And that is what is required for big O. Okay, that's what the definition means. You got to find these two things and show that c times n cubed is an upper bound for this function as long as we're using n's bigger than n naught. Yeah? Or equal to. So that, my friends, is the real mathematical proof. And now we're on to this slide, which when I cut back, it will have no writing. So you're going to watch me write all this again. So I will see you in the past again. So that's the idea. And let's do another example now. So let's pretend that f is just a random function whose domain is that and whose target is that. Makes sense. That's what is required for big O to work. Let's show that if we have f being big O of n, then f is automatically big O of n squared. Interesting. We know nothing else about f, but we know that it's O of n. So we assume this, prove this. Okay? To show. So, okay, proof. Let's do it. Let's do it real this time. Let f be O of n. That means, unwrapping this definition, we have there exists a c and n naught such that, let's see here, for n greater than or equal to n naught, f of n is smaller than, it's bounded below by c times n, because that was the original function. Okay? So we know that. We need to show now that it's also bounded by this. Okay? So, that's the idea. Let's do this. So, okay, let's keep the same c. Okay. We're going to show that f is O of n squared. So we need to show, to prove the thing, that there is another n naught. There is an n naught prime or something. There exists that, and such that f of n is less than or equal to c times n squared for all n greater than or equal to n naught. Well, look what we have. Dun 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 dun. It should usually, if n, notice, if n naught, and it should be, n naught is greater than or equal to 1, and it should be, dun dun dun, notice that Cn is less than or equal to c times n squared. It's always true, because if it's 1, they're the same. If it's 2, this one's obviously bigger. Yeah? That's the game. So we can actually use the same n naught. Otherwise, we can make it at least 1. It should be 1, in theory, if it's nothing else. Okay? So that is the idea. Here is use the same c, and we could keep the same n naught, even, if it's already greater than or equal to 1. So, therefore, f of n equals O of n squared, using the original c, and using c equals c, the first one, and this n naught equal to the old n naught, c prime equals c, the new n naught equals the old n naught, how about the maximum between the old n naught and 1? That should always work. And that is the proof. Okay? We notice, this was the big deal, that this is true when, for all n greater than or equal to 1, and I shouldn't have had the naught there, but as long as n naught itself started us off at 1, and it should have, this is always going to hold. And so using this and this together, we get that f of n is less than or equal to c times n squared. Okay, that's how we're doing it. So that is the idea if we multiply by n. Okay, so yeah, that is the game, and I think we have proved that this is O of n squared. Beautiful, huh? Okay, another example. Are you ready? So let's let f of n be this. It's n over 100. It's a function. Prove that it's not true that f equals O of square root of n. Interesting. And I guess we should use proof by contradiction to do that. Okay, we need to prove that it does not exist. There's no c, there's no n naught that will let this be bounded above by O of square root of n. Okay? So proof by contradiction is like, okay, let's assume that it is. Assume f is O of square root of n, and so there's a c, and n naught, such that all that other stuff that that O of n requires. Okay, we know then therefore that, I guess I do have to spell it out, such that let's see here, f of n is less than or equal to c times square root of n for all n greater than or equal to n naught. Okay, and this was just n over 100, and now we have to show that this is not true always. Okay, well, let's pretend we had a number. Let's find a contradiction now. Let's make it so that this was not the case. Okay, so here we go. N over 100, and we need to find values where this is not true. C square root of n. How can we do that? How in the world are we going to do that? Well, let's try and get the n's on the same side. If we divide by n and then multiply by 100, this can be turned into n over square root of n to the 1 over n to the 1/2 is square root of n. All right, and then that's less than or equal to 100c. Okay, now this is supposed to be true as long as n is greater than or equal to n naught for giant values of n. And so, well, let's square both sides. 100c squared. This is saying that n must always be less than this, where c is a constant. That's never true, okay? But c is a constant. So that can never happen, okay? And that's a contradiction. And we've just proven that it's impossible for square root of n to bound this. And it makes sense, I think. This is linear, this is, so n to the 1, and this is n to the 1/2, which is smaller than n to the 1. It can't be an upper bound. Okay? It is a lower bound, though. And what do you know? We have notation for that, too. So instead of big O, we can say big omega. Okay? And this is just about the same as big O, except things get swapped. You swap less than or equal to with greater than or equal to. That's all you do. Okay? We say f is big omega of g if there exists constants c and n naught such that f of n is greater than c times g to the n whenever n is greater than that n naught. So they eventually meet, and then c times g to the n is always smaller from then on out. Okay? That's the idea. So that's beautiful. It's a lower bound. G is a lower bound this time, because we want to bound on both ends eventually. So this means that if you have this function, 2n to the fifth, that is definitely lower bounded by n to the fifth, because you could choose c to be just 1, and it will be lower. Then it's also n to the fourth, big omega of n to the third, because those are smaller values, okay? These are lower bounds. That's the point, okay? That's big omega, and we didn't have to spend much time on it because it's essentially exactly the same as big O. Big theta is where it's at, though. This is where, if anybody, like, in real life ever tells you to use big O, they really mean big theta. They really want big theta, okay? Just in case no one's ever told you that before. Big theta is very similar to big O, but not quite. It's the tightest possible upper bound, but it's also a lower bound because of that. So let's talk about it. So big theta, capital theta. You might have seen theta like this before, where they're like theta versus that. There's like a gap between now. That gap is because it's capital. This was a lowercase theta. Now you know. Okay. Yeah. So f is big theta of g if it's both big O of g and it's big omega of g. Okay, it's bounded above and below by the same function. The constants can change though. So alternatively, you can pick two different constants, c1 and c2, and another n naught, such that this is true. c1 times g is less than f. It's bounding f below, and c2 times g is bounding f above. Okay, whenever n is greater than n naught. So it's an upper bound and a lower bound, which means it's the tightest possible bound, we like to say. Okay? So for example, here's our n naught, and from then on out, c1 times g is smaller, it's a lower bound, and c2 times g is bigger, it's an upper bound. So g itself, g is doing all the hard work, it is bounding f of x, and this looks like DNA now, which is cool. Okay, that's all. That's really it. So this means you only have one option now. When you have this function, there's only one other function that is both big O and big omega of that one. Okay? That is only n to the fifth. Okay? That is the idea. Oh, sorry. And then f of 2 to the fifth is only n to the fifth, and then this one is only n squared. 2n squared is only big theta of n squared. It can't be any others because then it loses the upper bound or the lower bound part. Okay? If you made this just n, now it's no longer an upper bound. It is a lower bound now. That's the idea. Okay? So there's only ever one option for you now when you have a function and you're trying to get the big theta of it. It's only n to the fifth. You can't choose a smaller or a bigger exponent. It doesn't work. It's impossible. It has to be both big O and big omega. It's quite nice. Okay? So yeah, just remember, anybody who's asking you for the big O complexity doesn't want a giant number. They want the tightest possible bound for that function, which is really big theta. Okay? That is my spiel. And now let's do this, and then maybe this one too, and then we'll get out of here. Okay, so let us characterize the rate of growth for each of these functions by giving another function such that it's big theta. Okay? So give it a try, and let's do it. So this one, it's essentially you can follow the big O rules. That's the idea. You really can. You just need to make sure that it's the tightest possible bound. Okay? So, for example, log n grows a lot slower than log n. Okay? On average. Log. It makes the number even smaller. Just with a hand wave, believe that. Okay? So, that's much smaller than n log n. Okay? And then the 9 can go away. So this is big theta of n log n. And whenever we use log in computer science, usually we mean log base 2. Okay? Really, it's log base 2. The base doesn't really matter. And so for this one, it's n log n again because you have to bring these out. Okay? And you can just say n log n, and this doesn't matter. Because you remember like how to convert between log base 2 of x and like log base 3 of x? You just like multiply one by the other. It's like, I don't know, something like involving log base 2 of 3 or something. I don't know if that's correct, but you get the idea. And this is just a constant. So you can just say log without any base, because you can convert by multiplying by just a constant, which we get rid of. That's the idea. Okay, the base doesn't matter. And okay, how about these? This is a trick. I'll show you soon why it's a trick, but I want you to code this up to notice that it's not n to the 21 that's winning. It's 1.1 to the n that's winning. This is exponential. This is polynomial. This one's the bigger one. Okay? So I'll show you rules soon. I have a table for you, but it is big theta of 1.1 to the n. Okay? That is the idea. And so this is exponential. It's very interesting. Okay, how about this one? 23n plus n cubed minus 2, boop, boop, is n cubed. Okay, so you're slowly learning the process. I haven't given you the full table yet, but hopefully you got most of these. Okay, the table is down here. We'll get there in the next lecture. Okay, time for this one now. And oops, sorry, I lied. The other one was way too hard. We're going to do this one instead. So let f of n be this, and prove that it is big theta of n cubed by finding these values. Find the C1, find the C2. Prove that it is big omega. Prove that it's big O, okay, of n cubed. That's the idea. So instead of like coming up with, because we need to do this algebraically, it's a better idea to come up with C1 and C2 ourselves, okay, to use algebra to get us there. So let's do the lower bound first. So we need to find something. We need to find some number. We need to find a C, like a C1, such that C1 times n cubed, because that's what we want, is less than or equal to n cubed plus 3n squared plus 4, as n is greater than some n naught that we'll find later. And the idea is we could just pick 1 here, because when we pick 1, this goes away, right? And this is totally true. N cubed is less than or equal to this, as long as n is greater than or equal to 1, right? Or even 0 because of this constant here. So this is always true. N cubed is always smaller than than itself, plus these two other positive things, right? That's the idea. It's always going to be true that this is true. And so we can even take n. It works even when n is greater than or equal to 0. Okay, so that works when that's true. So this is a potential n naught. 0 is a potential n naught, and C1 is 1. Cool. Let's find C2 now. Let's find the upper bound. Okay, so we have to find some number such that n cubed plus 3n squared plus 4 is less than or equal to C2 times n cubed, because that's what our upper bound should be. It's going to be big O. Okay. Now we need to find this number. What in the world can this C2 be? And the idea is, let's start with this. Okay, let's start with this. N cubed, and there's a trick. N cubed plus 3n squared plus 4. Watch this. Let's just convert these to be, instead of n squared, make it n cubed. Instead of 4, let's make it 4n cubed. N cubed plus 3n squared plus 4n cubed. And this is always true as long as this works. N is greater than or equal to 1 this time. Can't have it be 0, because then we would have gotten rid of the 4. Okay, this is totally true when n is greater than or equal to 1, and that's just less than or equal to 1, 4, 8 n cubed. And for free, we just found that this is less than or equal to 8n cubed when n is greater than or equal to 1. So let's let C2 be 8, and n naught is the bigger of these two. This one works when it's when n's greater than 0. This one works when n's greater than or equal to 1. So n naught better be greater than or equal to 1. Okay? And so that is Therefore, we've proved the omega part. Therefore, we've proved the big O part. And therefore, we've proved the whole thing, the big theta. Okay? So f is indeed big theta of n cubed. We've found the actual things. We've done actual algebra to prove that thing. Okay? So that's it. This was a good place to stop. Sorry, we probably went over a little bit of time, but this was the better place to stop. And then the next time we meet, we'll talk about how to actually use these topics, use these numbers, these systems to find the complexion, find the complexity of actual algorithms. So do look forward to that, and I will see you there.